for the scaled quantity T star, right? Then regardless of what the surface temperature is and the temperature far away is, I already know what is T star, so I just need to convert it to T using the scaling. Okay.
Yeah.
And that same solution for temperature, I can also use it for concentration, for velocity, and so on, right?
Yeah. All these things are analogous to each other.
Provided they are scaled.
Yeah.
On the other hand, if I did it in original variables, I could not do that.
Yes, sir.
Right? So you want to scale it in such a way that all quantities vary over roughly order 1 variation, let's say 0 to 1 or something like that, so that the solutions that you can get a universal solution. And then, if you have one problem where you have one set of boundaries temperature specified, that same solution can be used for that. The temperatures change, you can use the same temperatures again, same solution again, because you just have to change the scaling. You don't have to solve the problem all over again.
Yes, sir. Now I got this, means why you are using scaling the temperature or any quantity.
Yes. Yeah. Okay. On the other hand, if you're doing it in original variables, right, you don't know if you solve it for one particular set, that same thing cannot be applied for another set of boundary conditions, or for another fluid with a different diffusivity or conductivity, and so on, right? Whereas once I've scaled it, the problem becomes independent of parameters, right? So I just have to re-express the scaled parameters in terms of the original dimensional parameters. I don't have to solve the problem all over again.
Yes, sir. Got it, sir.
Yeah. Yeah. Okay. Any other questions?
Sir, give me a minute, sir. Okay. Sir, in the case of finite domain, means actually I was not getting the plot of temperature profile, means for the transient profile and the steady profile. For the steady profile, you draw. We know that at the steady state, it becomes uniform.
It is so for finite domain it is linear.
Yeah, it was linear. Yeah, but for the transient,
yeah.
Actually, I was confused in that. Means.
Okay, so we were solving it using separation of variables, right? So
yes, sir.
I can share a screen. You can see my screen?
Yes, sir.
Okay. So this is the finite domain. Okay, so the final temperature was this one, right? That was the final temperature, right? So
yes,
this
sir.
was T star is equal to the steady part is 1 minus Z, right? That was the final temperature, right?
Yes, sir.
The initial temperature was that T star is equal to 0 everywhere. So if I plot the initial temperature, it will look something like this. It will basically be 0 throughout the domain. At the bottom surface alone, you have instantaneously increased the temperature. Okay, so that instantaneously increased temperature, this is T star is equal to 1. And T star is equal to 0 throughout the domain. Okay, so that's the initial temperature. So in between those two, it's going to go through a series of profiles that look something like this. So as time increases, basically you'll get this kind of a progression, okay, as time increases. And that is what we had calculated using separation of variables. Okay, is that clear?
Yes, sir.
And that was that summation, right? So if I recall correctly, it was T star is equal to 1 minus Z minus sigma over N of 2 by pi N sine of N pi e power minus N pi the whole square T. Right? That was the solution. Right?
Yeah, this was.
Yeah. So if you plot the solution as a function of Z at different instants of time, okay, this is the solution that you'll get. And the second part is the transient part. Okay. The second part is the transient part. Okay. Do you know how to use in this MATLAB or anything?
No, sir. Actually, I know only about Python coding.
Okay. You know how to do C or C++?
Yes, sir. I have some knowledge in C.
Because you should be able to program this formula in quite easily and get these profiles.
Okay. Sir, one thing about as we have derived this function solution, we were checked. We checked like first with we equated it to a constant, and then we checked first constant was a positive number, and then we used it like minus alpha square.
Yes, yes.
And then we did the derivation. As in the first case, we have only trivial solution, and we are searching for non-trivial solution.
Yes.
That's why we did minus alpha square.
Yes.
But I want to ask that how we choose the value of minus alpha square.
See, because if you look at the what I don't recall what symbol I'd used. Right? What did I use for that? 1 by f of t df by dt is equal to 1 by z of z star. That we had written as minus alpha square, right? If I remember right.
Yes, sir.
Right. Now you take this part, okay? 1 by f of t df by dt star is equal to some constant, right? So this will imply that if I integrate it, if I substitute, I'll get df by f is equal to c dt, right? Okay.
Yeah.
Or logarithm of f is equal to ct plus some constant d, right? So I'll get f is equal to e power ct times some constant log of e power d. Okay.
Yes, sir.
This e power d, I'll call it as a. Okay. I'll call it as a, right? Now this f, if c is positive, it's going to increase exponentially, right?
Yes.
But then f has to go to 0 as t goes to infinity because the transient part has to go to 0, right? You have to get the steady state solution.
Yes, sir.
Right? So c cannot be positive because otherwise it keeps increasing exponentially.
Yeah.
So it has to be negative. Yeah.
But for the when we are using it like negative, means when it was negative, then how we used at is like n pi, means
Oh, n pi was because the solution that we got was z was equal to sine
is
of alpha z, right? Right? Into
yes,
a,
sir.
right? That b was
It was
0,
a sine alpha z.
a sine alpha z, right?
Yes.
So we know that z has to be equal to 0 at z star is equal to 1, right?
Yes, sir.
There is a boundary condition on top, right? It's a homogeneous boundary condition on top, right?
Yes, sir.
So either a can be 0 or sine of alpha z can be 0, right?
Okay, yeah, I got it from here.
So if you plot the sine function, right, that means that this implies that sine of alpha has to be 0.
Yes, sir.
If you plot the sine function, sine of alpha versus alpha, right, this is going to go to 0 only at this pi, 2 pi, 3 pi, etc. Right? Those are the only discrete locations at which it will go through 0. Okay.
Yes, sir. That's why we used alpha equals to n pi, and
Yes.
then we solved.
Yeah.
Yes, sir. Got it, sir. Everything. My doubt was
Okay.
cleared.
Fine. Okay. Yeah. Okay. Very good. Yeah. Thank you.
Yes, sir. Thank you, sir.
Thank you. Yeah. Okay. Fine. So I think this is the only question that we had. So can we close the session now?
Yes, sir.
Yeah. Yes, there is
There's only one student and he is
he's left here.
cleared with his doubt so that we can
Yeah.
wind up the session, sir.
Okay. Fine.
Yes.
Thank you. Yeah.
Thank you, sir.